Good afternoon and welcome to the second day of the Global EV Charging webinar event on EV charging best practices and power quality. Yesterday the focus was on best practices for EV charging in general. This day we will zoom into the subject of power quality. There are still two presentations left after this one. It's still possible to register for those ones via our website. All the webinars will be recorded and uploaded later on to our YouTube channel. So keep an eye on our YouTube channel, ElaadNL. Please subscribe to receive notifications. During the presentations, Tim Slangen and I will be hosting the webinars. And during each webinar, one of us will be the host. The other one will be monitoring the questions log. And we'll select questions to be answered after each presentation. You can find the questions box in the GoToWebinar tool. There's also a chat log, but please don't use that for questions, just use the question box. And this event has been made possible with support from the Progresses project. This project is supported by the Horizon 2020 program from the European Union, and it's focusing on improving efficiency and grid integration of the next generation energy supply infrastructure for electric vehicles. And now I would like to introduce you to our next presenter. It's Zian Qin, Assistant Professor in Delft University of Technology. And Dr. Qin is an IEEE senior member, and his research interests include wide bandgap devices, power electronics-based grid, and Power 2X. And Zian will present about the power quality of EV charging stations and looking from a power electronics perspective. So Zian, please go ahead. The floor is yours.
Thank you, Thijs, for the invitation and also introduction. Can you see my screen?
Yes, we can see your screen.
Okay, perfect. So yeah, let me. Sorry, I have to. Yeah, okay, perfect. So yeah, let me skip the introduction and just go directly to the outline. So first, I'm going to talk about the trend of EV charging. After that, I will talk about the definitions, also a showcase of the power quality issues. Then I will talk about the IEEE and IEC standards. After that, I will elaborate the current practice and challenges in the power quality study of EV charging. In the end, there will be a wrap up. So as you know, the majority of the mobility is still based on fossil fuel, but fossil fuel is going to be exhausted in one or 200 years. And also the emission is creating significant environmental problems. Therefore, we have to find a replacement of it. Batteries and hydrogen are the two most promising candidates that people are talking about. But even with the state-of-the-art technology, hydrogen is still far less efficient than a battery. I'm talking about the conversion between hydrogen and electricity. That's why battery-based electric vehicles is still the choice in the first place for e-mobility. And also in the last few years, electric vehicles as percentage of the newly sold cars in Netherlands has increased a lot. In 2020, it was 24.8%, and the target is to achieve 100% by 2030. It is also estimated that in the next 10 years, the electricity consumption by electric vehicles is going to increase a lot, not linearly, but exponentially. The different charging modes are also a share of different charging modes are also going to change in the next 10 years. In general, the charging mode, so-called AC level 1, is going to reduce. The charging mode AC level 2 is going to remain more or less the same. Meanwhile, the DC charging is going to increase a lot. Different charging modes have different charging power. In general, the DC charging has higher power than AC charging. So this is a definition is according to the standard SAE J1772. The charging modes are defined differently in another standard. but still it is quite similar. And it also tells that when the charging power goes high, it's going to be DC charging. A few charging standards have been developed in different regions, including CHAdeMO, developed in Japan, GPT, developed in China, CCS Type 1, mainly in North America, CCS Type 2, mainly in Europe, and Tesla, developed by Tesla company. All these charging standards can go more than 100 kilowatt charging power. There is also a new charging standard named Chaoji, which is a collaboration between CHAdeMO and GPT. In the future, it's also going to be compatible with IEC and CCS. And with this new charging standard, the charging power can go up to 900 kilowatt. And according to ING's survey, 15 minutes charging time can make the electric vehicles comparable with fossil fuel-based cars. So 15 minutes is like you arrive in the charging station, you plug in the charger, you go to take a coffee, then come back, you drive your car away. So there's you cannot really tell the difference between electric vehicles and fossil fuel-based cars. In order to achieve 15 minutes charging time, the different electric vehicles requires different charging power. For instance, it is 69 kilowatt for Mini Cooper and all the way up to 228 kilowatt for Tesla Model S. The main limit factor of charging power for the electric vehicles is the battery. There are already a few battery technologies that can achieve 4C charging rate. So 4C charging rate is roughly means 15 minutes charging time. There is even a charging technology that the battery technology that can achieve 9C charging rate. So these are the demands for 15 minutes charging time. Questions: are there already electric vehicles that can handle such high charging power? The answer is yes. For instance, Porsche Taycan can achieve up to 270 kilowatt charging power, which is much higher than the demand, which means the charging time can be even shorter than 15 minutes. And there are also a few commercially available chargers that can already do the fast charging job. So it seems like electric vehicles are already ready for the fast charging, and chargers are also ready. But whether the grid is ready for massive installation of ultra-fast charging stations is still a question mark. To figure it out, a big European funding has been granted to a large consortium. In this project, our role is to study the power quality of EV charging station, where we deeply collaborate with ElaadNL. There are different kinds of power quality issues, but talking about EV charging, we mainly focus on flickers and harmonics. Typical harmonics are those components that have frequency that are the integer multiple of the fundamental frequency. So the frequency range of the typical harmonics is in 100 Hertz to 2 kilohertz. Interharmonics is within the similar frequency range, but the component have a 9-integer multiple of fundamental frequency. Superharmonics are those components whose frequency is in the range of 2K to 150 kilohertz. Beyond 150 kilohertz, that is EMI. And actually, Helco already has given a very nice presentation on this topic. Flicker is kind of voltage fluctuation because the frequency is very low. Therefore, if such a voltage is used to power a light, a human being is able to notice the fluctuation by eyes. There are already a few power quality issues associated with chargers that have been reported. For instance, flicker emission of 120 kilowatt charger at a bus station and super harmonics measured by ElaadNL on a few chargers. Flicker emission associated with this Tesla charger has also been reported, and you can find more details here in this link. So you may wonder, okay, since there are power quality issues associated with the EV charging, then what are the grid compliance that we have to follow regarding the power quality? The thing is, there is no grid standard that's dedicated to EV charging yet. I mean, power quality standards. But we think these power quality related IEEE and IEC standards are those we can refer to. And you can find more details about these standards in this survey paper. Okay, the next question is then, how can we study the power quality of EV charging? Before that, let's look at the layout of EV charging station. So if you want to connect the ultra-fast chargers to the grid, which means a few hundred kilowatts, then you have to you need a medium voltage grid connection. Then with a step-down transformer, it creates a low voltage AC bus. Then you can connect a few ultra-fast chargers to this AC bus. You can also use a centralized rectifier to create a low voltage DC bus. In this way, you can get rid of the front-end rectifier in the individual chargers. You can even go further to replace this transformer and the centralized rectifier with a power electronics converter, which is called a solid-state transformer. There is already some, let's see, a company that looking at this solution. But since the layout shown here is still the mainstream, so we decided to focus on this to study the power quality issues. Power quality issues means voltage or current issues on the grid side. Therefore, the details or dynamics of the second stage DC-DC converter in each charger can be ignored. It means we will just focus on this front-end rectifier in the charger. Usually they goes a modular design, which means you may have several sub-modules in parallel to handle big currents. And the topology of sub-module could be a Vienna rectifier, which is very widely used. It could also be a two-level rectifier. Or in some cases, if you want to save the cost, you can also go with a multipulse rectifier. In order to study the power quality issues, the system can be equivalent to such a circuit. To be more specific, the charger side actually means the front-end rectifier of the charger can be equivalent to a current source in parallel with the input impedance of the charger. While the grid side can be equivalent to a voltage source in series with the grid impedance. So as you can see, power quality issues at PCC can be affected by all these four elements. So in order to study the power quality issues, first of all, you need to model all these elements. One way to do that is so-called black box measurement, which means if you have a charger, you can connect the charger to a grid emulator. Once the grid emulator is generating clean grid voltage, then you can, in the output current of the charger or input current of the charger, depending on how do you define the direction of the current, you can extract the harmonic current source. You can also use a grid emulator to generate some voltage perturbation. Then as a response, the charger is also going to output some current perturbation. Then the ratio between the voltage perturbation and current perturbation will be the input impedance of the charger. So this is a very effective and also very widely used way to model the impedance and also the current source of the charger. But the major drawback is when the current emission and the impedance is small, you can get very big error in the measurement. In order to get rid of the error in the measurement, another way is to model the circuit inside the box. So when you open the box of the charger, the thing that you will see can be elaborated by this schematic here. So on one side, you will have a grid voltage as input of the charger. On the other side, you will see the power stage of the charger. And in between, you have the EMI filter and also input power filter. Another very important part is control of this power stage, including a phase lock loop control, current control, the grid side current control, the DC side voltage control, and also the modulation. And it is found that the harmonic current source IC is affected by the voltage level modulation and also the filter. Well, the input impedance EC of the charger is affected by the power filter and the DC side voltage control, PLL, current control, and also sampling frequency. So the modeling of these two elements is actually the procedure that you try to express these two elements as functions of the parameters in the hardware and also in the control. The figures here, figure and the tables here shows how the different, different blocks affects the power quality issues in a different frequency range. So once you have the model of the chargers and also the grids, you can develop a charging station impedance model. And if you also have the load profile, or you may also call it the charging profile of the chargers, then you can evaluate the harmonics by once you get the current at the PCC point. You may also evaluate the flicker if you get the voltage at the PCC point. So with this impedance model, even even a typical harmonic evaluation needs 1 day continuous evaluation. It is still doable because you can have a large step time there, and this step time I'm talking about a few minutes. But the thing is, in this impedance model, I mean, in the simulation, you assume the impedance and also the current source, which represents the chargers, are time invariant. The thing is, but in fact, if the current source and also the impedance, they are both load dependent. Means when you charge the car, the charging power, if charging power changes, these two elements will also change. So if you in the evaluation you use fixed impedance and also current source, you may eventually get a very big error in the evaluation. Now, how do you solve it? Well, you may use the converter switch model. Then you load this converter switch model with the charging profile. Of course, the impedance you get from this model and also current source get from this model will be much more accurate. But you cannot use this model for, let's say, a 1 day harmonic evaluation because it's super slow due to the very short time step. So how do you solve this trade-off between the accuracy of the evaluation and also the simulation time or computational effort? Actually, we figure out a way, and we call it a multi-timescale simulation tool for harmonic evaluation. And this figure shows how it works. First, you start from the load profile or charging profile of the charger. Each time you take one operation point. Then you go to this converter switch model, make sure the converter is operating at that specific operation point. Then you extract the current source and also impedance of the charger. Then you input this, let's say, time variant impedance and also the current source into the impedance model of the charging station. Then you will be able to evaluate the harmonics in a short period of time. And after this 5 minutes, you go back to the load profile and take another operation point until you finish this load profile. And in this way, you get both good accuracy of the evaluation and also relatively shorter simulation time. And to give you an idea, with this approach, we are able to, let's see, evaluate the harmonics of the charging station with 1 day load profile in, let's say, 2 hours by using a normal computer. So if you want to make it faster, you can choose, let's say, a more powerful computer. Then it's going to be less than 2 hours. So Flickr, we have also done some study about how the Flickr can be affected by charging. And we figure out that the Flickr can actually be affected from several aspects of charging, including the startup power, the ramp time of charging, short circuit ratio of the grid, the grid impedance phase angle means whether it's more resistance or more inductance can also influence the Flickr, and also the status of other chargers in the same station when you let's see start charging with this charger. Of course, later on we will see how can we use this information to coordinate between the different charging events in order to reduce the Flickr. I'll wrap up. So in this presentation, I hope to give you an impression that fast EV charging is really demanded because the passengers they want a short charging time. They want let's see 15 minutes instead of 1 hour or overnight, and it is really coming. The charging mode standard, charging standard, EV batteries and chargers are ready. I mean, not all of them, not all the chargers are ready for ultra fast charging, but they are already of ultra fast chargers that can do the job. And studies on the grid impact of the fast EV charging are of high importance in order to ensure a stable and clean grid, even when the massive fast EV charging stations are connected to it. It is, I mean, at this moment, there are already fast EV charging stations, but when we talk about massive installation, means the installation will be doubled, tripled, or even much more. So in that scenario, can the grid still be stable and clean? That's the major research question that we are looking at. Power quality evaluation is very time consuming with current practice. And we have developed a multi-time scale simulation tool to solve this problem. Last but not least, it is found that the power quality of EV charging is affected by the grid condition, the design of the EV charger, but also the operation point, which means the instant charging power of the charger. So the operation point of the charger is in general a demand of the EV, but it is technically set by the charger, right? For instance, if the EV demand, let's say 100 kilowatt, but the charger can only do 5 kilowatts, then eventually it's going to be 5 kilowatt instead of 100 kilowatt. So which makes it possible to properly set the operation point of the charger according to the grid condition to implement so-called grid-friendly smart charging. But how to do it, that is going to be our future work. Okay, so in this last slide, I would like to acknowledge my PhD student Lu Wang. He helps a lot to prepare this presentation. And due to the time limit, I couldn't go through too many details in the presentation. But if you are interested, there is a survey paper which includes all the details, and the paper is a collaboration between us and ElaadNL. And it is open access, means no matter if you are a subscriber of IEEE, you can get it for free. Thank you. My presentation ends here. Thank you for your attention.
Thank you, Zian. It was a really interesting presentation. Really liked how you gave a nice overview of these different converter topologies, how you can measure them, how you can model them, and use them in your simulations, and actually also some results that comes out of some of these simulations already. So really interesting. I have a question myself regarding well, converter topologies. For actually new materials that are being used for new types of converters, like gallium nitride. I was wondering if that would somehow change the change the power quality of these kind of converters.
It depends. If let's see if the gallium nitride is used to replace the silicon-based IGBT, but if you are still using the same topology, then I would say the approach will still be the same, but one parameter might change. That's the switching frequency, right? I mean, it doesn't make sense if you still stick to the same switching frequency if you use gallium nitride. But if you look at the higher frequency, because gallium nitride switching faster, so it has a higher dV/dt, so it may create let's see, more significant noise at higher frequency, but maybe that frequency range is already in the range of EMI. Yeah, so that is maybe the area of other researchers. Yeah, so what matters, including the topology of the converter, switching frequency, of course, and also let's see how fast the switching is, means the dV/dt. So all these things matter. Yeah.
Oh, okay. Yeah. What are the benefits, by the way, of these higher switching frequencies?
So in general, you want to push the switching frequency in order to shrink the passive components, right? So if the switching frequency is higher, then you need a smaller filter. That's I would say that's a straightforward benefit of this higher switching frequency. But other than okay, then the influence on efficiency, I would say, okay, if you use gallium nitride or silicon carbide, you may get higher efficiency, but not because of a higher switching frequency, right? I mean, that is the trade-off between them. So yeah, so it's a kind of several factors coupled together. Then you need to think about what do you really want.
Okay.
Yeah.
Thank you. And another question, we're wondering if it's actually possible, or it's becoming possible, to actively filter high frequency emissions to send us a signal to compensate for these kind of distortions, the superharmonic distortions.
I mean, if let's say for switching frequency noise or those noise that's the integer multiple of the switching frequency, what you can do is, or what is already been done is, maybe you put several power modules in the operation of interleaving. Means they have the same switching frequency, so they will have the noise at same frequency. That's clear, and also same magnitude. But if you interleave them, means you on purpose shift their phase so they can cancel out with each other. And actually, when we are talking about the ultra fast chargers, a very widely used approach is to put several some modules in parallel to interleave them. So that's why when you measure it, the noise at switching frequencies are actually very low. So yeah, so the so with this interleaving approach, you can very effectively cancel out the noise at switching frequency.
But, yeah, excellent. That sounds like a really smart way to handle this. Yeah.
Yeah. For the superharmonics, I mean, so far I'm not quite sure about the course of the superharmonics. It is still, I mean, still a lot of research needs to be done. Once we figure out the course of the superharmonics, we may find a way to further mitigate it.
Yeah. Okay, excellent. We have two questions at the moment from the audience. First question from Zian. Well, thanks for the great presentation, he says. Does your modeling scenarios include multiple electric vehicles charging at the same time, each at a different operation point?
Yes, it does, because the model actually takes into account the operation point. So when you use this model for the, let's see, power quality evaluation of the station with multiple chargers, you can set them at different operation points. Then it is considered. Yes.
Okay, good to know. And another question from Paul Broos. For fast charging, the power will build up rapidly. Yesterday, a person from the CPO Allego, that was Martin Jaspers, mentioned that the MV-LV transformer DSOs normally use are not suitable for big load variations. What impact may this have on the power quality on the grid?
I would see. Okay. Yeah. Okay. I would see the major effect is maybe the if you are talking about the ramp up, then it is mainly the flicker, because there is only one ramp up during one charging event, right? So as if you can you still see my screen?
Yeah.
As you can see here, so with let's see, with shorter ramp up time, you get larger flicker there. But I think the question is also talking about what's the short circuit ratio of the transformer, right?
Yeah, he's specifically talking about the transformers, that they are not suitable for, well, big load variations. So it must have something to do with overheating, I guess. But
okay, then I would see because every transformer has some impedance. If you see it is not good for large load variation, then maybe because the impedance is relatively large. Therefore, when you have a big load variation, you will have some big disturbance on the voltage caused by this impedance.
Yeah, of course.
Yeah.
Indeed. Yeah. And that might result into flicker or some other effects on the electronic devices on the grid. Yeah.
Exactly.
Okay, excellent. Now all this information you shared, it is also accessible via the IEEE website.
Yes.
And can all these things be found here, like the modeling and the simulation and
the model, if you are talking about the impedance modeling, it's not in that survey paper yet, but there will be more publications coming out, and you can find details of the modeling there. You can find something in our EPE paper, which is mentioned here, about the details of the modeling.
Okay, yeah. Excellent. I think that might be very interesting for our attendees. Okay, well, I see we don't have any further questions. Well, is there any final message you would like to well, give to the audience? Maybe about some next steps or developments that you think that are important to well, better integrate this chargers into the grid or something? Just go ahead.
For sure. I mean, we are just at the beginning of this beginning of the study of EV charging power quality issues. So we have some achievements, but there's still much more that needs to be studied. I mean, no matter if you are EV charger manufacturers or the grid operators, if you are interested, we are very happy to collaborate. Yeah, so you have my contact information in the last slides. So you may give me a call or drop me a message if you are interested, and I'm always happy to talk about this. Thank you.
Yeah, excellent, and indeed, please do, because well, we can't tackle this issue ourselves, of course. So we really need to come together and solve this to prevent issues in the future, of course. Well, excellent. Well, thank you for your presentation. It was really insightful. Really learned a lot today. Hopefully the attendees did too. There are still 2 presentations left today. Next one will be Jill. We will be presenting about RCDs, the influence of well, electric vehicles, DC chargers on those. And the final presentation will be by Tim Slangen. We'll present about our research on well, electric vehicles and DC chargers and their power quality emissions. So I hope to see you all again during these final 2 presentations, and well, have a nice event.
Thank you, guys. Thank you.